Okay, we're going to continue our study of Unit 3334, Open Book Test. The directions where find all relative extrema. Use the second derivative test where applicable. Okay, so number 8, we're going to rewrite this as an exponent so that we can find the derivative. So we know that that's going to be x squared plus 1 raised to the 1/2 power, the square root to the 1/2 power. We're going to find the first derivative. So we take the exponent, 1/2, we have a chain rule, 1/2 times the guts of the function, reduce the exponent by 1, so we take the derivative of the wrapper, the derivative of the function, and that's what we've done, times the derivative of the guts of the function, or what's inside our parenthesis wrapper there, the u, if we use the u terminology, 2x. Okay. The negative is going to place that in the denominator, and the half is the square root, so we would have f prime of x is half of 2 is 1 of those little x's, and then the negative is going to place that in the bottom, and it's going to be a square root. So square root of x squared plus 1. Now, we want to find the critical numbers, and the critical numbers are where the numerator x equals 0, or where there's an undefined situation. Now, there's no value of x that we can plug in there because and get a negative under the square root, because when you square any number, positive or negative is positive. So there's no way to get a 0 or a negative in the square root, so we're never going to get an undefined situation from the denominator. So we have only one critical number, x equals 0. Now, instead of setting up test intervals in the first derivative, we're going to apply the second derivative test. We know that at x equals 0, there is a possible relative max, there's a possible relative min, and there's a possible point of inflection. So at that, one of those three things could possibly be going on. So we're actually looking for relative extrema, so we're hoping that at that 0 there's a possible max or min, but we'll find out. And the way we can find out is we can plug that critical number into the second derivative and check for concavity. We know that if in the second derivative it's concave up at that critical number, then there's going to be a minimum point there. And if in the second derivative at that critical number it's concave down, then there would be a relative maximum at that critical number. And if at that particular point it was neither concave up or concave down, it's right at that point where it changes concavity, then there would be a point of inflection there. So we're going to do the second derivative so that we can plug our critical number into it and check for concavity at the point. Okay, now to do that, we're going to go ahead and take this first derivative and rewrite it in exponential form. So we're going to have x times x squared plus 1 raised to the negative 1/2 when we move it back to the top and write the square root as an exponent. And then we're going to take the derivative of that. Now, we've got multiplication, and then because of the parenthesis, we have a chain. So we need to apply the multiplication rule and the chain rule. So f double prime of x. Now, the multiplication rule says you take the first times the derivative of the second. When we do the derivative of the second, we have a chain. So we have exponent negative 1/2 times what's inside the parenthesis wrapper. We call it the guts of the function, or the u. We're going to reduce the exponent by 1, which will give us a negative 3/2. Negative 1/2 minus 1 whole, which is 2 halves, will give us negative 3 halves there. Okay? So we've got first times derivative of second, but we haven't finished the second. The second's a wrapper, so we've taken the derivative of the function. Now we need to take the derivative of what's inside that wrapper, and the derivative of x squared is 2x, and the derivative of that 1 is 0, so it goes out. So that's the first part, first times derivative of second, and then we're going to have plus the second, which is the x squared plus 1 to the negative 1/2, times the derivative of the first, and the derivative of x is 1. And so we have this expansion. As we look at that expansion for factorable possibilities, there's a plus sign, which means we can factor out of each of the two terms there. We see a common base of x squared plus 1. And so we can factor out some exponential value of that common base. And what we always factor out is the least of the two, the least of the those common values. And the least exponent between negative 3 over 2 and negative 1/2 is negative 3 over 2. There's no other common factors on the left and right, and so we're going to factor out that common base of x squared plus 1 raised to the negative 3 over 2. So we're going to have that times whatever's left from those other two terms. Over here we have a negative 1/2 times the 2 is a negative 1 times an x, which is a negative 1 understood x squared. And then recall, when we think about this times what will give you that we think when we multiply with like bases, we add the exponents. And we know that if we added a 2 over 2 exponent to a negative 3 over exponent, it would give us a negative 1/2 exponent. So every single time when we deal with the chain rule situation, the multiplication rule and the chain rule, that it happens that what we would be multiplying is by this base to the first power. See that 2 over 2 is 1. And it's going to be that times a 1, which is that. And so we're going to have a plus x squared plus 1. Now, we can simplify those x squares that go out. And so we're going to have f double prime of x is. And this term, this expansion is going to go to the bottom because of the negative. So what's going to be left on top is just this other factor of 1. We're going to have 1 over, and then that's going to go to the bottom. And then let's talk about that 3 over 2 power. I'm just going to use a number as an example. Let's say we had 7 raised to the 3 over 2, for example. Now, the 3 means to cube, and the half means square root. So we could write that as 7 cubed, and then take the square root of it. Or we could think of it as the square root of 7, and then cube it. We oftentimes like to make the square root a wrapper. It really doesn't matter. Thinking of that, then we can take this x squared plus 1. And then we can think of the 3 part of it as being a cubing of it. And then the 2, the denominator, being a square root. So we have 1 over the square root of x squared plus 1 cubed. Now, remember what we were trying to do. We were trying to take a look at this critical number. We want to plug it into the second derivative to check for concavity. If it's concave up at that point, then that's a relative minimum. If it's concave down at that point, it's a relative maximum. And the way we check for concavity is to see if it's positive or negative in the second derivative. Well, if I put in a 0 for x right here, I'm going to have 0 squared is 0 plus 1 is 1. 1 cubed is 1. The square root of 1 is 1. So what I have is a positive 1. over a positive 1, and we're really just looking for positiveness or negativeness. So that critical number, when plugged into the second derivative, is positive. That tells me that at that point, the graph is concave up, giving us the idea of concave up. And if it's concave up, then at that point, there is a relative minimum. There's a relative minimum. So at the point 0 something, there's a relative minimum. Now, for us to find out what that something is, we need to go back into the original function. We want to find the function value at that critical number 0. So we're going to have 0 squared plus 1, which is equal to the square root of 1, which is 1. And so at the point 0, 1, on the original graph, the graph of the original function, we know that there is a relative minimum. All right. Now, let's kind of try to verify this when we think about a square root graph. Our mind would go back to the parent function of a square root graph, and we would think, okay, we've got f of x equals square root x, and in our mind we're thinking it does something like that. But what we have here is the square root of an x squared something, and we get the idea that a square cancels a square root, but we still got that 1 there. So it's kind of like we've got an x situation. But we've had all this squaring and square rooting, so we think, well, what does that do? The fact that it turns into an x means it flattens it out. See, that's linear. So we have some kind of a linear idea going on, but we've got all this positive and negative, plus or minus square root or the square. And so what happens with all that plus or minus? So we may be a little bit confused in our mind that what's it going to turn out to be? It's got the square root, so but then it's gonna cancel and got an x. So let's go to the graph and take a look at this so we can see what it turns out to be and verify graphically that there is a relative minimum at 0, 1. So we're going to go to our graphing calculator, and we're going to go to y equal. Now we want the square root, so we're going to do second x squared for square root of, I'm going to get my variable x, and then I need to hit the square, and then plus 1, and then we'll close parenthesis, and we'll hit graph. And what we have is something that looks kind of like an absolute value. Kind of an interesting graph, but we can see graphically that at the point 0, 1, there's a relative minimum. Now, it sort of appears that this thing is more of a linear situation, but when we look at here, we actually can see some curving. If we zoomed in a little bit, we could verify if it's actually exactly straight. Some of that may be in the way that it's the pixelation. Let's kind of do a little zoom in. Let's change our window just a little bit and kind of see what that gives us. Let's do our window from -3 for x to +3. Just kind of play with that a little bit. Let's do our minimum y of, we'll just go -1 because most of the graph is up high. And then let's just go to a +3. And let's take a look at the graph there. Did you see we kind of do have some kind of curvature going on. So it's not didn't actually exactly flatten out like an absolute value. Kind of turn it into some kind of cross between a parabola and absolute value almost, it looks like, somewhere between. Kind of interesting graph we get, but again, we can verify that there is an absolute minimum here. All right. Well, we summarized then in 3.3 and 3.4. We took the first derivative. We looked at the critical numbers. We set up test intervals and we checked for increasing, decreasing. We know that if it goes from increasing to decreasing, and I'm going to remove that so I can kind of show you. We talked about if in the first derivative test, if it's positive, then it's increasing. If it's negative, it's decreasing. If it's going from increasing to decreasing, then at that critical place, there must be a relative maximum. Or if it goes from decreasing to increasing, at that particular point, if it goes from decreasing to increasing, there must have been a relative minimum. So then we talked about the fact that if we took the second derivative, and we took our critical number from our first derivative, we plugged it straight into the
We need
second derivative.
FFA officers for meeting, please. FFA officers in the ag shop for a meeting. Also upward bound in the library. Upward bound in the library.
Negative in this first
Students, if you
derivative,
brought me
which
a
means that it is
note
not
yesterday
taken
from
down.
Harris Regional Medical Center, it did not have a name on it. If you brought me an excuse note from Harris Regional Medical Center yesterday, you need to come by the office.
If in the second derivative at this critical number, we would find.
Excuse me, talent search. This is talent search in the library, not upward bound.
And being that it's concave up, we could verify that at that point there's a relative minimum. All right, thank you.